So to answer these questions right here, it's important for us to take a look at what the formula is for an electric field and more specifically what it means. We've got K, which is a constant. So there's two variables we're going to plug in. We have our Q and we have our R. Now, the Q here is going to be the charge. Okay, and that is a result of really what makes the electric field. So if you have two plates like this, and you have a negative end here and you have a positive end here, you know you're going to create a magnetic or an electric field this way. Now, if we were to increase the charge, well, that would affect the electric field. So you can see there's a ratio between, I'm going to say example 1 with the electric field and Q1, and field 2 and Q2. So if we were to double the charge, and I'll just reverse these to make this easy, that means that we would go from 2 to 1 over E2 over 3.2 times 10 to the 2. So therefore, this would have to double. Our answer for the electric field would be 6.4 times 10 to the 2 newtons per coulomb. Because what have we done? We have increased the charge of these plates right here. That, of course, will make a stronger electric field. Now, the R right here. Some of you are going to be tempted to do the same thing because we're saying triple here, so we want to plug in a value of 3 here. But that's not what the R is referring to. The R in this equation is referring to where is our test particle in the electric field. So for example, if I was to call this X here, well, this blue particle would experience a force of a distance of X towards positive, and then a different force over here, which I'll call Y. That's what the R's are referring to, is where we are relative to one of the plates. If we were to take this plate right here and move it, well, remember, what makes an electric field? What makes an electric field is the charge between this positive and the negative plate. It's the density. So the answer is if we triple the separation, there is no change to the electric field.